Number of possible roots. Welcome, everyone. Before we dive into today's new topic, let's quickly recap what we've already covered. In our previous lesson, we established that a root of a quadratic equation is simply a value that, when substituted into the equation, makes the equation true. Specifically, we are looking for values of x that satisfy the equation at x squared plus bx plus c equals 0. Now, as we begin our discussion on the number of possible roots, a very fundamental question arises. How many such values can actually exist for a single quadratic equation? Is it possible to have 1, 2, or even many more? To answer this, we look at the structure of the equation itself. Because a quadratic equation is a polynomial of degree 2, the number of roots it can have is mathematically limited. Specifically, what we need to keep in mind is that a quadratic equation can have at most 2 real roots. This means you might find 2 different answers, 1 single answer, or even no real answers at all, which is exactly what we are going to explore in detail over the next few slides. Categories of roots. Now that we understand that a quadratic equation can have at most 2 roots, we need to look at how we can actually classify these solutions. You'll see that depending on the specific values of the coefficients, which we call a, b, and c, the solutions will always fall into one of 3 distinct categories. We are going to explore each of these 3 scenarios, 2 distinct roots, 1 repeated root, and no real roots, in the next few slides. 2 distinct real roots. Now that we know there are 3 possible categories for roots, let's dive into the first and most common scenario, 2 distinct real roots. In this case, you are looking for 2 different real numbers that, when plugged into the equation, make it true. When you look at the equation in its factored form, you will see 2 different linear factors. Let's look at a concrete example to see how this works in practice. Consider the equation, x squared minus 5x plus 6 equals 0. To solve this, we follow 3 simple steps. First, we factorize the quadratic expression. We are looking for 2 numbers that multiply to 6 and add up to -5. That gives us x minus 2 all multiplied by x minus 3 equals 0. Second, we apply what we call the zero product property. This is a fancy way of saying that if 2 things multiplied together equal 0, then at least one of them must be 0. So, we set each part to 0. Either x minus 2 equals 0 or x minus 3 equals 0. Third, we simply solve for x from the first part. We get x equals 2, and from the second part, we get x equals 3. So, to conclude, we can see that this equation has 2 distinct real roots, 2 and 3. This is a perfect example of the first category we discussed, where the solutions are 2 separate, unique values. 1 repeated root equal roots. Now, moving on from our first case where we had 2 different answers, let's look at our second category. Sometimes, you'll encounter a situation where the quadratic expression is what we call a perfect square. In this specific scenario, the 2 linear factors we use to solve the equation are actually identical. Now, don't let that confuse you. Even though we technically have 2 factors, because they are the same, they both lead us to the exact same numerical value for x. Because of this, mathematicians refer to this outcome as a repeated root, or sometimes a double root. Let's look at a concrete example to see how this works in practice. Consider the equation x squared minus 6x plus 9 equals 0. First, let's perform step 1, which is to factorize the quadratic expression. When we factorize this, we get the quantity x minus 3, multiplied by the quantity x minus 3, which can also be written as the quantity x minus 3, all squared, equals 0. Next, in step 2, we solve for x since both factors are the same. We only need to solve the single equation, x minus 3 equals 0. This brings us to step 3, our result, which is x equals 3. So, to reach our conclusion, even though we started with a quadratic, we don't have 2 different answers like we saw in the previous slide. Instead, the equation has just 1 repeated root, which is 3. This sets the stage for our next case, where we will see what happens when there are no real solutions at all. No real roots. In some instances, you will encounter an equation where there is simply no real number that you can substitute for x to make the equation true. This happens mathematically when the quadratic expression cannot be factorized into real linear factors, meaning you can't break it down into two simple brackets using real numbers. Let's look at a concrete example to see why this happens. Consider the equation x squared plus 1 equals 0. To analyze this, let's follow a simple process. First, we isolate the variable by subtracting 1 from both sides, which leaves us with x squared equals -1. Now let's look at the result and analyze it. Think about the nature of squaring numbers. Since the square of any real number, whether that number is positive, negative, or even 0, is always non-negative, it is impossible for x squared to ever equal -1. Therefore, our conclusion is that this equation has no real roots. Now, we have looked at cases where we have two different answers, and cases where the two answers are actually the same. But we must also consider the third category, no real roots. This concept might seem a bit abstract right now, so in the next slide, I'll use a real-world analogy involving the path of a ball to help you visualize exactly what no real roots looks like in physical terms. Real-world analogy, the path of a ball. Now, I know that looking at equations in algebra can sometimes feel a bit abstract. So, to help you visualize these three different categories we just discussed, let's step away from the chalkboard and look at a real-world analogy, the path of a ball. Imagine you are throwing a ball straight up into the air. The height of that ball at any given moment in time can actually be modeled by a quadratic equation. This is a perfect way to see our three cases in action. First, let's look at the case of two distinct real roots. Suppose you want to know at exactly what times the ball reaches a height of 2 meters. If you throw the ball up, it will pass the 2-meter mark once while it is ascending. That's on its way up. And it will pass that same 2-meter mark a second time as it is descending. That's on its way down. Because there are two separate moments in time, we have two distinct roots. Next, consider the case of one repeated root. Think about the very peak of the ball's flight, its maximum height. There is only one single, specific moment in time when the ball reaches that exact peak before it starts to fall back down. Because there is only one unique time value, we call this a repeated root. Finally, let's look at the case where there are no real roots. Imagine you are looking for the time when the ball reaches a height of 100 meters, but you only threw the ball 10 meters high. In this scenario, the ball simply never reaches that height. Since there is no possible time value that makes the equation true, we say there are no real roots. As we move to our final slides, we will summarize these key takeaways and address some common pitfalls to avoid during your exams. Key takeaways. All right, let's bring everything together and recap what we have learned today. First, it is crucial to remember the fundamental rule. A quadratic equation, which we write as a x squared plus b x plus c equals 0, can have a maximum of 2 roots. It will never have more than 2. As we explored through our examples, there are 3 specific scenarios you need to look out for. First, we have 2 distinct roots. This is when your solution results in 2 different real numbers, like the 2 separate times a ball passes a certain height on its way up and its way down. Second, we have one repeated root. This happens when the quadratic is a perfect square, meaning both factors are identical. In this case, the 2 roots are actually the same numerical value, much like the single moment a ball reaches its peak height. And finally, we have the case of no real roots. This occurs when no real number can satisfy the equation, such as when we try to find a height that the ball simply never reaches. Keep these 3 categories in mind, as they are the foundation for everything we will do next, especially when we start looking at how to identify these cases using the discriminant. Common mistakes. First, be careful not to assume that there are always 2 different roots. After seeing our examples of 2 distinct roots, a repeated root, and no real roots, it's easy to fall into the habit of expecting two different numbers every time. However, as we discussed in the slide regarding repeated roots, a single value can actually be a valid outcome when the quadratic is a perfect square. So, don't be surprised if you only find one value for x. Second, try not to confuse the term no real roots with no solution in a general sense. Now, if you continue into higher-level mathematics, you will learn that these equations can actually have complex or imaginary roots. But for our purposes here in grade 10, we are strictly focusing on real numbers. If you find that no real number can satisfy the equation, like in our example where x squared equals -1, we simply state that there are no real roots. Finally, never ignore the at most part of our definition. Remember, we established at the very beginning of this lesson that because a quadratic is a polynomial of degree 2, it can have a maximum of 2 roots. It is mathematically impossible for a quadratic equation to have 3 or more roots. So, if you're solving an equation and you end up with 3 different values for x, stop and recheck your work, because there is likely an error in your calculations. Now, as we wrap up this lesson, I want to pause and highlight a few common pitfalls that students often encounter when working with quadratic equations. Paying attention to these will help you avoid unnecessary errors in your exams. Keep these points in mind, and you'll have a much stronger grasp of the nature of quadratic solutions.